In this video, we're going to be looking at the concept of an antiderivative. An antiderivative is exactly what it sounds like. It's something that undoes a derivative. So, antiderivatives undo derivatives. And this is going to be the first step towards the concept of integration that we've spoken about a little bit in the past. And so we'll touch on that starting in Chapter 5 a little bit more formally. But this is going to be sort of our first step in that direction. So we've done examples in class where we looked at a position. We had a function that we specified the position of a particle as a function of time, and as we took derivatives of position, we got velocity. As we took the derivative of velocity with respect to time, we got acceleration. Antiderivatives are going to allow us to climb that ladder in sort of the opposite direction. I'll be able to go from acceleration up to velocity, and from velocity, I'll be able to take the antiderivative up to position. So that's going to be one of the sort of applications of this. Another application is that antiderivatives are going to allow us to study sort of the cumulative effect of some sort of quantity. And so we'll discuss these in detail, but the idea of an antiderivative and ultimately the idea of integration is that we're accumulating things and looking at the result of an accumulated quantity. So let me give you the definition that we're going to use for our antiderivative, and it'll introduce a little bit of the notation that we're going to use as well. So here is our definition. A function that I'll call capital F is the antiderivative of little f on some interval that we'll call I, so on an interval I, if when I take the derivative of the capital F, so f prime of x, if I wind up with the lowercase f. Everywhere on that interval. So for all x that belong to that interval I. So we're going to define an antiderivative in the context of a derivative. Basically what I'm saying is the antiderivative, this capital F, is the function that when you take its derivative, you'll get this lowercase f. So if I know this function, my goal is going to be to try to figure out what this function is. So if I know lowercase f, can we figure out the function that will spit out lowercase f as its derivative? And so we have some easy examples of this. If I tell you that f of x is equal to 2x, what is the function, capital F, that spits out 2x as its derivative? And in this case, we would say that the capital F, which we'll use for the antiderivative, is going to be x squared, because when I take the derivative of that, f prime of x, that's the same as d dx of our x squared, and we get 2x out of it. Similarly, if I have f of x equals x squared, what is the function whose derivative is x squared? And in this case, it's going to be 1/3 x cubed. We know that when we take the derivative of a cubic function, it'll become a quadratic, but we also need to make sure that the coefficient sitting in front is correct. This 1/3 will account for that. When this 3 comes down, If I did the derivative of just x cubed, I would get 3x squared. I don't want a 3 here. I want it to be a 1. So this 1/3 will account for that 3. They'll cancel out and leave me with the coefficient that I'm wanting, which is a 1 right here. So again, because f prime of x in this particular case is going to be x squared. That 1/3 again cancels the 3. But one thing I want you to notice is that these functions aren't necessarily unique. So going back to the example we just looked at, if I told you f of x was equal to x squared, there are multiple options for the antiderivative. One of them is the one that we just did. So we could have that f of x equals 1/3 x cubed. But I could also have f of x be equal to 1/3 x cubed plus 2. Because f prime of x, when I take that derivative, so when I take d dx of 1/3 x cubed plus 2, taking the derivative of the 1/3 x cubed will give us the x squared that we're looking for, and the derivative of the 2 will be nothing. It's 0. The derivative of a constant is 0. So this will give me the same x squared plus 0, which is really the same thing, right? That 0 doesn't change the x squared value. And it doesn't have to just be a 2 that I put here. It can, in fact, be any constant. And this is the most general way that we can write one of these. So this part I have no control over. It's going to be a 1/3 x cubed. But this part, we can also add any constant to that. This is going to be the most general antiderivative that we can come up with. So the idea is the following. If f is an antiderivative of lowercase f, so is f plus c. Where c is any constant. So let's run through a couple more quick examples just to get a feel for it. And this is really going to be how well do you know your derivatives. Being able to compute an antiderivative is really a question of how well do you know your derivatives. We've got to kind of have a pairing where we know a function and its derivative, and we'll just think of that about that pairing in sort of the reverse order. If I know a function and its derivative, here I'm looking if I can recognize the derivative, what is the original function. So for example, if I give you that f of x was equal to cosine of x, what is the function whose derivative is cosine of x? So capital F of x is going to be the function whose derivative is cosine x. So what is the function whose derivative is cosine? Well, in this case, we know the derivative of sine is cosine. So it's going to be sine of x, but then we've got to remember if this function is an antiderivative, so is this function plus any constant. So I'm going to add in my plus c. That is the most general antiderivative. So this is the most general antiderivative. And what we've done to generalize it was adding that plus c. So let's do another one. What if I give you f of x equals 1 over x? can we recognize the function whose derivative is 1 over x? So again, this is just a question of how well do we have these pairings down. And the most general function whose derivative is 1 over x is the natural log of x. And in fact, the natural log of the absolute value of x, because this works for both positive and negative values of x now. And again, to make it as general as possible, we need to add our plus c. So we just need to recognize function, derivative, function, derivative. And we're just trying to do it in the reverse order. If I did a general power rule, if I wanted x to the nth power, what is the antiderivative of x to the nth power going to be? Well, I know it's going to be 1 power higher, so it must be something times x to the n plus 1, because when I take the derivative of x to the n plus 1 according to power rule, the power will be reduced by 1, which will give us the power that we're looking for, which is just n. But this n plus 1 will come and sit down in front of the function as the derivative, and I don't want that because there is no n plus 1 sitting over here. So to undo that n plus 1, I need to do a 1 over that n plus 1. So I can think of this as 1 over n plus 1, sitting right there. And again, to make it as general as possible, I have to add my plus c. So this is essentially power rule right here for antiderivatives. This is going to be an important one to remember. Okay. With this in mind, I want to come up with some more general kind of rules for all of this. How do they work? We'll see, again, more carefully in Chapter 5 that we'll have a way of defining these antiderivatives. In fact, we'll phrase them as integrals at that point. But we'll have a way of showing what they look like in terms of a limit. Just like we had a limit definition of a derivative, we're going to have a limit definition of an integral. And so a lot of the same rules that applied to derivatives also apply to integrals, in the sense that they're all come from sort of the limit laws. So for example, so we'll have a couple of rules that these things can follow based on the limit laws. One is that if we have a function, so let me write down, here's the function, and over here we'll have the antiderivative of that function. If my pen will work, okay. So here's the function, here's the antiderivative. If the function isn't just f of x, but is instead some constant times f of x, it turns out that constant will be sitting there in the antiderivative as well. It kind of passes through, so to speak. Because if I were to take the derivative of this, what do you do when you have a constant times a function and you take the derivative? That constant just passes through the derivative, so it's going to pass through the antiderivative as well when we go in the reverse order. If we have a constant here, we'll wind up with a constant and its derivative. If we have that constant in the original function, that constant will show up in its antiderivative. This is kind of the idea. Similarly, if we've got a function that's made up of more than one function, so if I've got an f of x plus a g of x over here, that'll correspond to some capital F of x plus some capital G of x. The derivative of this portion will yield the lowercase f, the derivative of the capital G will yield the lowercase g, and it's similar in the antiderivative direction as well. So essentially, what we're going to want to do is we can pair every derivative that we've computed this semester. With its antiderivative. We can come up with just this big list of pairings, basically. Everything that we know how to take a derivative of, if we know what that derivative looks like, we should know what the antiderivative looks like as well. So just keep that in mind. Let's do an example where we can put a few of these into play. So for example, if we know that I want to do the following. So let's say I want to find all the functions h of x such that h prime of x, the derivative, is the following. It's 2 cosine of x minus, let's say, like 3x squared minus 2 times the square root of x, that whole piece over x. This is an antiderivative problem because I'm interested in finding the original function when I'm given what the derivative of that function looks like. So the only thing we need to do is try to recognize what are the antiderivatives of these pieces. Can I break this into a bunch of pieces, or I can immediately recognize what the antiderivative looks like? So this piece is easy. We've already done this one. We know the antiderivative of cosine of x is sine of x, and we just saw, according to this rule right up here, that factor of 2 will just get carried over into the antiderivative. But this piece looks much uglier. However, if we realize that we can simplify this, break this into separate terms, we can rewrite what this looks like and break it into pieces that we will hopefully be able to compute the antiderivatives of. So let's do that now. So this first piece I'm not going to touch. It's still going to be 2 cosine of x. But this next piece, the 3x squared divided by x, I can simplify that. The x squared and the dividing by x, one of those x's will cancel, and I'll just wind up with minus a 3x. And then for the second term here, we have this minus out here, another minus here. Those are going to cancel and become a plus. I'm going to have that factor of 2. And I have a square root of x over x. So x to the 1/2 power over x to the 1st power. This ultimately is the same as x to the negative 1/2 power. Is what that term simplifies to. So now I've broken this ugly thing up into 3 relatively easy pieces to compute the antiderivatives of. So what we're going to get is that this implies that h of x, the function whose derivative looks like what we've computed right here, this first piece will be 2 times the sine of x. Right? That's the antiderivative of the 2 cosine of x. This one we'll do power rule on. In fact, we'll do power rule on both of these, but let's start with the 3x. So I'll have that minus 3. I'm not going to touch that for now. And the x, we have that rule from earlier. I know it's going to be an x squared, but if I were to take the derivative of x squared by itself, I would get a 2x, and I don't want a 2x. I want it to just be an x because I've already accounted for the minus 3 here. So to account for, so to make this piece when I take the derivative just be x rather than 2x, I need a 1/2 to undo that 2. So there's, oops, undo that. There's sort of the antiderivative of just that piece that is the x. And again, that's basically an application of this rule that we have up here at the top. We're just applying that sort of power rule for antiderivatives. Similarly, for this piece, I'll have my plus 2. I'm going to have x to some power. The power should be 1 greater than the current power. So if it's negative 1/2 here, the power here should be positive 1/2. But when I take the derivative of this, I'll get a 1/2 x to the negative 1/2. I don't want that 1/2. So I've got to undo that 1/2 with a factor of 2. Or essentially you could think of it as a 1 over 1/2. But an extra factor of 2 here would give me the appropriate x to the negative 1/2 when I take this derivative. The 1/2 will come down and cancel the 2, and then the power will decrease by 1 to negative 1/2. And this 2 is this 2 here. So just to make it totally clear, this piece goes with this piece, and this 2 I put here to make sure that there's essentially, you can think of as a coefficient of 1 sitting in there, essentially. That's kind of our idea. Okay, and now it's just a matter of remembering that we're looking for, so we can see the whole thing, we want to find all the functions. So essentially we're asking for the most general solution, so I can't forget my plus c. And then after that, all we need to do is simplify. So simplifying, that first term is unchanged, 2 sine of x, can't get simpler than that. That next one, I'll just combine those coefficients into a negative 3/2 x squared, and that last one will become a plus 4 x to the 1/2. You can write it as an x to the 1/2. You could also write it as a square root of x if you prefer, plus c. So there's our most general solution. All we've done is taken something that I didn't immediately know what the antiderivative looked like and tried to break it up into pieces where I could figure out what the antiderivative of those simpler pieces look like. So this is going to be one of the major ideas of solving these types of problems. It's also going to be something that we do. We've talked this semester about solving differential equations. This same idea is going to apply when we solve differential equations. I'm not going to focus on that here, but let me just write that down. The same process will apply when solving differential equations. But if you think about it, when we found this function up here in the last example, and we said we're really finding all functions, if I find something that has the derivative I'm looking for, so let me give you a little sketch to illustrate this point. Maybe I decide that here is the appropriate function. This is that h of x from the previous example. But because it has this generic plus c here, this function right here also works. Here's some h of x, maybe minus a 1. And maybe up here, here's an h of x plus 1. And maybe down here, here's an h of x minus 2, or minus some other constant. So here's my x and my y coordinates. All of these have different values of sort of, if you want to think about this one, you could think of it as plus 0. So these all just have different values of c. Different values of c. All of them have the same derivative because the derivative is the slope. All those lines drawn right there have the same slope. All have the same slope and therefore the same derivative. So if we are working on a differential equation, for example, where we're trying to find which is the appropriate h of x to use, we'll have to have some additional condition given where we specify some specific point, and maybe we say this point. So specify a point. Oftentimes this will be given as something called an initial condition. In the context of a differential equation. But you specify a point and it determines the value of c that we should use. So looking at this, there's only one of these curves that happens to go through this point. this is the unique solution that happens to go through this particular point, and maybe this point would be specified as some important condition we're wanting to meet in the problem. So just keep this idea in mind. We will need additional information. So the main idea is that we need additional info to determine a specific value of C. And we can do an example to illustrate this idea. So let's do one now. I want to do another example. So here's our example. Same as before, I want to find f, the function f, if giving you the derivative, if f prime of x is equal to the following. It's e to the 2x plus maybe 12 times 1 minus x squared plus, let's do cosine of x again. And if I tell you that f of 0 is equal to 1. So this is going to be that initial condition or that additional piece of information that we'll use to determine what the value of C is for this problem. So to figure out this problem, I need to rewrite all of these pieces into something that I can take the antiderivative of. This one's close. This one I should distribute, so I've got an e to the 2x plus 12 minus 12x squared, just distributing that 12 through, plus cosine of x, and that's the function that we're trying to take the derivative of. So that's going to imply that the antiderivative, f of x, is, so let's think about this one. We haven't done an exponential yet. What is the function whose derivative is e to the 2x? Well, I know exponentials spit themselves out, so it's going to be some sort of e to the 2x. But if I were to take the derivative of e to the 2x, I'd get e to the 2x, and then by chain rule, I'd have e to the stuff times the derivative of the stuff, where that stuff is the 2x. That would give me an extra factor of 2. I don't want an extra factor of 2, so to account for that, I'll put a 1/2 to cancel that 2 that we'll get. And now, when I take the derivative of this piece, I'll get e to the stuff, so e to the 2x times that extra factor of 2, and that extra factor of 2 will immediately cancel with this 1/2 to give me the coefficient that I actually wanted up here, which was a 1. So that's the idea. There's the antiderivative of e to the 2x. This is why it's important to be able to do those sort of quick chain rule problems where it's just a matter of a constant like this. To be able to do those in your head, it makes these antiderivatives much faster. This one, I've got a constant plus 12. You can think of that as x to the 0. This is just going to be 12x. The derivative of 12x is 12. This one over here, we've done a quadratic before. We know it's going to be some sort of x cubed. So write this down. Let's see if we can figure out what this coefficient needs to be. When I take the derivative of this, I want this coefficient to wind up being a negative 12. So I know I'm going to need a negative sign. I'm not going to get that from the power, so I need a negative sign. Let me write that 3 a little clearer. Okay. So I'm wanting, when I take the derivative of this, the 3 will come down, the power will go down to 2. I'll get an x squared like I wanted, but I want the coefficient to be a negative 12. Right now, if I brought the 3 down, my coefficient would be just negative 3. I need something that's 4 times bigger than that. So if I just put a factor of 4 right here, I have found the correct coefficient in my antiderivative so that now when this power comes down, I will get a negative 12, like I wanted here. and then the power decreases by 1, so I'll have x squared. I'll get negative 12 x squared. And lastly, that plus cosine, we've already done that. The derivative of sine is cosine. And lastly, we need our plus c. So this is the antiderivative. And now I want to use this condition to figure out what is the specific value of c that will satisfy this particular condition. So essentially, I've got, just like we did here, I've got a big family of all of these different curves. They all look, whatever this curve looks like, plus some constant. And I'm trying to pick out which is the appropriate one by specifying what f looks like when x is equal to 0. So what the y output is when x is equal to 0. So let's do that. Let's plug that in. F of 0 means I just need to replace every single x by 0. So this becomes a 1/2 e to the 2 times 0 plus a 12 times 0 minus 4 times 0 cubed plus the sine of 0 plus c. And all of that's supposed to be equal to 1. Right? F of 0 is supposed to be equal to 1. So going through piece by piece, thinking about what all of these different pieces are, that whole piece is 0, that whole piece is 0, the sine of 0, if you remember your trig functions, the sine of 0 is 0. I've got my plus c, and this piece over here, I have e to the 0. E to the 0th power is 1, so this whole piece turns out to be a 1/2. And that's equal to 1. So when it's all said and done, plugging in that condition simplifies to something where I've got the situation looking like the following. I've got that 1/2 plus c equals 1. And what does that mean that c needs to be? So I'd subtract a half from both sides, and I'd find that c also needs to be equal to 1/2. So we get, for our final answer, that our f of x is equal to 1/2 e to the 2x plus 12x minus 4x cubed plus the sine of x, just copying from the line here, plus c, but we just found what the c needs to be in order to satisfy this condition. C has to be a half, so plus 1/2. And there is the final solution for this problem. Let's try another example, just to make sure that we're kind of on board with this. And then I'll talk about sort of a more applied version of this same problem in just a minute, relating it to actually to physics. So we're not just doing all of these sort of toy problems here. So let's try this one. Let's see if we can do it in 2 steps. I want to find f. So I want to find our function f, but now instead of giving you f prime of x, I'm going to give you f double prime. So I'm going to give you the second derivative. F double prime of x is equal to, in this case, 12x squared plus 6x, plus cosine of x minus e to the x. And to get from f double prime to f, I'm going to have to take 2 antiderivatives, right? We're talking about, I want f. I've given you 2 derivatives of f. So we're going to have to find the antiderivative of this, and that'll give us f prime, and then I'll have to take the antiderivative of that to get f. Each time we take one of those antiderivatives, we'll introduce a different plus c. So I'll call the first one that we get c1 and the second one we get c2. But that means if I want to get a unique solution here, I actually have to specify 2 conditions. So I want to tell you that f of 0 is going to be equal to 1, and f of 1 is equal to 5. 2 conditions we need those two conditions to solve for those two constants. So that is our idea here. Okay, so first things first, let's find that antiderivative of that term right there. The antiderivative will be just one f prime, and so we will go from f double prime to f prime. And in doing that, we've got, let me just go up, we've got a lot of the same terms, similar to stuff that we just had in the problem a minute ago. So this one's going to be a 4x cubed. Write that one down because we don't need to see them all again. So the first term, the 12x squared, became 4x cubed when we take the antiderivative. The derivative of this will give me the 12x squared. For this one, I'm going to get plus something that's an x squared. Taking the derivative of this, I would get 2x. I don't want 2x, I want 6x. So what do I need here? I need an extra factor of 3. And now when I take this 2 down, it'll multiply the 3 and give me the 6 that I'm looking for. The cosine of x, we've done a couple of times. It's sine of x. And then this e to the x is easy. No chain rule necessary. This is just minus e to the x. And the last thing that we need, again, to make this as general as possible, is plus a constant. And I'm going to call that constant C1 just because, again, in a minute, we're going to do this again and introduce a second constant, which we'll call C2. So let's do that now. I want to figure out what f of x looks like. So let's take the antiderivative of the stuff that we just found. I want to start with that 4x cubed term. The antiderivative of that 4x cubed term is going to be equal to something that's an x to the fourth. And in fact, in this case, it's just going to be x to the fourth because this is set up. So this is set up. I apologize, my phone is going off here. Thought I had it on silent. Okay. So doing this, going back to this, when I take the derivative of x to the fourth, the 4 will come down, the power would go from 4 down to 3, and I would get 4x cubed. So that term is done. Similarly, this one, I want to figure out the antiderivative of 3x squared. I know it's going to be something times x cubed. And right off the bat, when I take the derivative of x cubed, this factor of 3 will come down, and I would get 3x squared. So I've got that piece. The antiderivative of sine. I know that cosine of x, when I take the derivative, it gives me sine, but it actually doesn't give me sine, it gives me negative sine. So to account for that negative sign, I need to replace this plus with a minus. The antiderivative of sine is negative cosine. This is one that people confuse a lot. When I take the derivative of cosine, I will get negative sine. If I don't want a negative here, I need to make the original cosine be negative to cancel that negative and give me the positive that I'm looking for. And lastly, this last piece will be minus e to the x. One other thing to keep in mind is as we took the antiderivative, this was a constant. We haven't figured out that constant yet because we don't have f yet. We'll find it in a minute. But when I take the antiderivative of a constant, I can't ignore that piece. This is c1 times x. When I take the derivative of c1 times x, I will just get the constant c1. And the very last piece is we need our second constant because we've just taken a second antiderivative. So there's our c2. So this is the most general form of f of x, and it has two constants in it, c1 and c2. We'll now use those two equations to figure out what c1 and c2 are. So the first one, looking at our conditions, we try to keep my formatting similar. So we've got these guys. F of 0. Well, that's just 0 to the fourth, which is 0, plus 0 cubed, which is 0, minus the cosine of 0 minus e to the 0 plus c1 times 0 plus c2. And that's all supposed to be equal to 1. So looking at all of these pieces, that one's 0, that one's 0. In this case, the cosine of 0 is 1. And so we have a minus 1 here. E to the 0 is also 1, and we also have a minus sign there, so we're going to get another minus 1. This term is just 0, and we have plus c2 equals 1. So at the end of all of this, I've got c2 minus 2, accounting for both this minus 1 and this minus 1, is equal to 1, which implies that c2 must be equal to, adding 2 to both sides, it must be equal to 3. So now we have that f of x, we've solved for one of the constants, f of x is now x to the 4th plus x cubed minus the cosine of x minus e to the x plus c1x, because we haven't solved for c1 yet, plus c2, which we just found is 3. So that's what our f of x currently looks like. And now we'll do the same thing that we did a minute ago, except for now I'm going to evaluate this at 1, f of 1, using my second condition up here on the right. So f of 1 equals 5. So f of 1, plugging that in, I will get 1 to the 4th power plus 1 cubed minus the cosine of 1, which I have no idea what that is, but that's fine, minus e to the 1 plus c1 times 1 plus 3. And that whole thing is supposed to be equal to 5. And so if I look at all the pieces that we've got out of this, try to simplify it, I've just got a 1 plus a 1 minus the cosine of 1 minus e to the 1 is just e, plus c1 plus 3 equals 5. And our goal is to now solve for that c1. So let's isolate that c1. I've got a 1, so here's all those pieces. Hopefully that's pretty clear. It's a little wonky. Whatever, good enough. I've got a 1 plus a 1 plus a 3, that adds up to 5, which I can cancel with the 5 on this side. So what we get out of this is going to be negative cosine of 1 minus e plus c1 equals 0, having canceled those 5s. So I basically said cancel that, that, and that with all of that. Solving that for c1, we would just add the cosine term and the e term to the other side, and we would get that c1 is equal to e plus the cosine of 1. And we'll just leave it like that. E plus the cosine of 1. It's ugly. I don't know what the cosine of 1 radian is. You could get a decimal approximation on a calculator if you wanted, but this is good enough. And what we finally get, our final result, is the following. We find that our f of x is equal to x to the 4th plus x cubed minus cosine of x minus e to the x plus c1 times x, where c1 is e plus the cosine of 1. So there's our c1 times x plus 3. There is our full solution. based on that going from a second derivative to the original function. Okay, so now let's apply this same idea to a physics problem. So in physics, we assume the acceleration due to gravity is constant, at least near the surface of the Earth. We've talked about this before. If you're taking a physics class, you'll be familiar with these numbers. If you're doing it in meters, it's 9.8 meters per second squared. If you're doing it in feet, it's about 32 feet per second squared. And so we'll use this for our projectile motion problem. So for us, we will use that the acceleration due to gravity is going to be 32 feet per second squared. And because it's downward, we'll put a negative sign in front of it so that it's clear that the acceleration due to gravity is making things come down. So let me give you a word problem that has to do with what's called projectile motion. We've done some of these before, but the idea of projectile motion is just something shot up into the air, and we're sort of following its flight path through the air. So in this case, it's going to be a cannonball. So a cannonball is shot upward, so straight up, at a speed of, at least initially, that speed is going to be 96 feet per second. And it's coming from the top of a castle. So from atop a castle, 128 feet above the ground. I want to come up with an equation where we can find the height after t seconds. And later on, maybe we can answer some other questions. So basically, I'm looking for h of t. Maybe we'll just call it, in this case, we'll think of it as the following. So from acceleration, I should be able to take the antiderivative and get velocity. And from velocity, I should be able to take the antiderivative and get position, which we're calling height in this case. So this is kind of the path that I want to go through. We've done these problems before, but I always gave you the height, and then we took the derivative to figure out what the velocity was, and took the derivative of that to figure out what acceleration was. In this case, we're going through this in a more natural order. On Earth, acceleration due to gravity is negative 32 feet per second squared. And when I take the antiderivative of a constant with respect to t, so this thing here, this is dv dt, and I want to figure out what the v is. So acceleration is dv dt. What does that mean the velocity v is? Well, it's going to be negative 32 t, that's the antiderivative of a constant. You get a linear term, a first order term, plus that first constant. And this is now our expression for dh dt, the height, the position. And I want to figure out what the position is by taking the antiderivative of this. So how do you take the antiderivative of this first term? Well, it's a power of t to the first. When I take the antiderivative, I know it's going to give me something that involves a t squared. And now I just need to figure out what the coefficient is here. So when I take the derivative of this, I would get 2t. I don't want 2t, I want negative 32t. So to get that negative 32, I'll need a negative here. And I'm doubling some number to try to get 32. That number needs to be 16. So in this case, when I pull this 2 down, when I take the derivative, I'll get t to the first power, and this factor of 2 will come down and turn this negative 16 into a negative 32. So this is the antiderivative of that piece. What is the antiderivative of this constant? Well, constants are easy. We just did it for the 32 a minute ago. This is going to be c1 times t. And then lastly, because we are taking the antiderivative again, we're going to introduce, just like before, a second constant, c2. This is now our height as a function of time. To figure out what these two constants are, we can use the information that's given in the problem. We're given 2 pieces of information, one about the initial velocity and one about the initial height. And we can use those 2 to find C1 and C2. So, for example, now we're going to use the info in the problem to find C1 and C2. So the first one is they tell us the velocity at time 0. It's assumed, based on the wording of the problem, when they say that the ball is shot upward at a speed of 96 feet per second, that is what we're going to call t equals 0. When the cannonball leaves the cannon, that's going to be our t equals 0. And it tells us that at that point, the velocity is 96 feet per second. And so we also know, let me do this the other way first. I also have an expression for the velocity right here. And so I'm just going to plug in t equals 0 to that thing. It's negative 32 times 0 plus c1. And that whole thing, as we just saw a second ago, is supposed to be 96. And so this is really easy to solve. 32 times 0 is just 0. All I'm left with is c1, and c1 must be equal to 96. So it turns out that this constant, c1, that we just found, turns out to be our initial velocity. For all these projectile motion problems, this is going to be our initial velocity. So we have that. So far, we have, having solved for one of our constants, we have that h of t, the height of this thing, is equal to negative 16t squared plus 96t plus c2, which we haven't touched yet. The other information that we have is that the initial position. We also know that h at time 0, so the second that that cannonball is shot, it's shot from the top of the castle. And that castle is 128 feet up in the air. So plugging this in, I'm going to get negative 16 times 0 squared plus 96 times 0 plus c2. All I've done is plug in 0 everywhere that t showed up. So there and there. Plus c2, and that's supposed to be equal to 128 feet. So it's 128 feet above ground. Again, easy to solve. Those first 2 terms are both 0 and 0, and I just get that C2 is equal to 128. So, putting it all together, we get an expression for the height that h of t is equal to negative 16t squared plus 96t plus 128. And it has units of feet. In general, this number right here and this number right here, this will be the initial velocity, which we'll write as v of 0. This number right here will be the initial position, which we'll write as h, in this case, of 0, height. Notice we're only keeping track of the height. We're forgetting about that we're assuming this cannonball was shot basically straight up, and we're keeping track of just the height. We're not keeping track into how far this thing has traveled side to side. Okay, so here is our expression. What if, as a follow-up to this question, we asked, what time does it get to its, so how long does it take to get to its maximum height? So, when does it reach the maximum height? And maybe as a follow-up to that question, we can ask, when does it eventually hit the ground? So we'll ask that one in just a minute. So we want to find the maximum height. So basically, we are trying to maximize h of t, right? We've done these maximization problems. All we need to do is take the derivative, set it equal to 0, and that'll tell us our critical points. Then we can do a first or second derivative test to decide whether this thing is a max or a min. But in this case, it'll all be fairly straightforward. The nice thing is, taking the derivative of h of t and setting it equal to 0, that's just the same as setting the velocity equal to 0, which makes sense. We've shot this cannonball up. It's continuing upward, 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 but it's slowing down. So basically, let me draw a little thing over here. We shoot it up. It goes upward, 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 but it's slowing down. And right when it stops, that's the maximum height it gets to. And then it'll start coming back down and will eventually crash on the ground. And here it is from the top of our little, castle tower up here. Right, so here's our top of our castle. And here is the ground down here. So there's the max, and down here there is the ground. I want to know what t is equal to right here, and then what t is equal to right here. When does it get to its max height? And then in a minute we'll ask, when does it hit the ground? Okay, so, but notice right here it's when v of t equals 0. When the velocity stops, that must be when it gets to its maximum height. Okay, so we have that expression already. We already have the velocity. We just need to find, so h prime of t equals v of t. But we already found that. And we want to set it equal to 0. So v of t is, going back up to our expression, it's right up here. And we've already solved for C1. We found that C1 was 96. So the velocity is negative 32t plus 96. Oops. Undo that. Undo that. Okay. So negative 32t plus 96. There's our velocity, and we want to set it equal to 0. And now when we solve for t, we would move maybe the negative 32t over to the other side to make it positive, divide both sides by 32, and we will find t is equal to 3 seconds. So solving for that one, t is equal to 3 seconds. We want to check if this is a max or min. We can do that really easily here with the second derivative test, because v prime of t, taking the derivative of this, the second derivative of the original, so h double prime of t, which is v of t, is just a of t, the acceleration. And the acceleration we already found is negative 32. We know it's negative. If it's negative, we get a sad face, and that means that we're dealing with a max. So we've got a max by second derivative test. Okay. Good. Last question. When does it hit the ground? So when does the cannonball, so we found that this top time up here in our little diagram, this turned out to be at 3 seconds. And now we're trying to figure out what the time is down here when it hits the ground. Okay. Well, in this case, we aren't trying to find a max or a min. We're just trying to find the time that it hits the ground. We need to know some information about what it means to hit the ground. So what does it mean to hit the ground? Well, when it hits the ground, the height is 0, right? We're assuming that this is a height of 0 at the ground, and the top of the castle, that was the height of 128 feet. So I just want to know, when is h of t equal to 0? So when the height is 0, that's when it hits the ground. So I just need to set h of t equal to 0 and solve. Our h of t, going back up, we've got it written right here. I just need to set this thing equal to 0. So we've got, let me just write it down, negative 16t squared plus 96t plus 128 is supposed to be equal to 0. That's what we're trying to solve. We just need to solve for t. Obviously it's a quadratic. It'll give us 2 values of time, but one of them would be the hypothetical time that the cannonball would have left the ground to have passed through the height of the castle right here, 128 feet, at t equals 0. So one of them is going to be a negative time. The other one will be a positive time. The positive time will be the one that we're going to look for. First things first, I'm going to simplify these coefficients. If I divide every single term here by this negative 16, all of these turn out to be divisible nicely. So I can divide everything by negative 16, and I'll get that t squared minus 6t, so 96 divided by 16 is 6. And this last one, 128 divided by 16 is going to be 8. So minus 8 equals 0. And we can either try to look for 2 numbers that are going to multiply to 8 and add to negative 6. Multiply to negative 8 and add to negative 6. But we're not going to actually be able to find one. I'm just going to use the quadratic formula. This is not a nice integer value of time. So the quadratic formula, again, says that t will be equal to, in this case, negative b plus or minus the square root of b squared minus 4ac all over 2a, where a, b, and c are respectively the coefficients of the first, second, and third term, a, b, c. So for us, what we're going to get is negative b, so negative 6, plus or minus the square root of that negative 6 squared, there's my b, minus 4 times a, which is 1, times c, which is negative 8. All of that over 2a, which is just 2 times 1. So those are the 2 values. We can simplify these numbers. This is going to be 36. We'll be adding 32 to that 36. I think that'll give us, what, 68. So I will get positive 6 from these signs canceling, plus or minus the square root of 68, all of that divided by 2. It turns out this is divisible by 4. We can pull that factor of 4 out, and it's going to be 17, I guess. So 6 plus or minus. Pulling that factor of 4 out, outside of the radical, it becomes a 2. So 2 root 17 over 2. Cancel the 2's with this and the 3, and we will get 3 plus or minus the square root of 17. The negative version yields a negative t. The positive version is our answer. So it hits the ground. Whoa. Hits the ground at t equals 3 plus root 17 seconds. You can do decimal approximation of that if you would like. So this is the idea. What is an antiderivative and how are we going to use them? In the next couple of sections, we're going to start focusing on the idea of integration, how it relates to antiderivatives, and how we can start to deal with more complicated things where we don't just have an immediate pairing right off the bat that we recognize here's a function, here's its derivative, or here is the function and here is its antiderivative. So we'll see that in the next video.